Howdy, howdy. This is Mr. Potter. In today's lesson, we're going to try and round up the testing for convergence we've been talking about throughout the latter half of chapter 9. So we're going to be talking about alternating series test as one of our other workhorses that we use in conjunction with the ratio test. And we're also going to be talking about true intervals of convergence. And I make this true comment as opposed to the intervals of convergence that we did earlier in chapter 9. These true intervals of convergence, we actually say what happens at the endpoints. Because as we noticed, when we do integration of some series, we actually gain the boundary points. And so the question arises, when exactly do we gain those boundary points? But I want to start first by talking about the alternating series test, because there are types of series that tend to follow very basic rules. And this is also one of those series where if I can figure out these three qualities, then I know that it's going to converge, and it's pretty easy to show that. So we've got the alternating series test. So normally we've been talking about a series where n starts at some value of k going to infinity of a sub n. But in order to show that it really is an alternating series, I want to start the series as n goes from k to infinity of negative 1 to the n times u to the n, where un is some positive unit. And my alternating series test actually goes through three steps. One, the first step is that u sub n is greater than 0 for all n. In other words, this truly is an alternating series. This term is always going to be positive, and the sign is uniquely determined by this negative 1 to the n aspect. So u sub n needs to be positive for all n. The second thing is that these terms do need to be getting smaller. In other words, u sub n has to be greater than u sub n plus 1 for all n greater than n. In other words, there's going to be some point where every term after this is going to be smaller. And it's okay if the first 6 terms, or the first 10 terms, or the first 100 terms don't satisfy that. As long as for some starting point, every point beyond that does. And the third is that these terms really need to be headed towards 0. And if they aren't headed towards 0, then I'm kind of violating the nth term test. But this is just kind of a safeguard to make sure that these terms actually do get progressively smaller smaller, but also approach zero. Because it would be possible to have a series like this and this that violated this because these terms were approaching a value of 1. So I might have a series that went like something like 3/4, then 2/3, then just something like that, where these terms get closer and closer to 1. So I want to talk about this. The thing is, if these 3 points all end up being satisfied, then our series of -1 to the n, u to the n, converges. In other words, just the fact that all of these terms are truly alternating and they get progressively smaller and they head towards 0, that's enough to show convergence, which brings us to some rather interesting facts. The harmonic series that we've been talking about extensively, this diverges. But as soon as I slap a -1 to the n in there, now it is 1 over n is positive for all values of n. Each term is bigger than the subsequent one, because 1/2 is bigger than 1/3, 1/3 is bigger than 1/4, and so forth. And these terms do approach 0, and this series, because it is an alternating series, and it satisfies each of these 3 conditions, this converges. So this kind of puts the p-test on its ear. As long as it alternates. And that's really the key here. So I could have a series like the sum from n equals 1 to infinity of 1 over radical n. And this diverges because of the p-test. But as soon as I make this an alternating series, as n goes from 1 to infinity, as soon as this is alternating, now we converge. And so it really is powerful the way that I can take a look at this. Just because my series ends up alternating, as long as it satisfies these 3 rules, then my series has to converge. So this is a really nice rule that we're dealing with here. So the next thing that I want to talk about is I want to talk about these true intervals of convergence. And so what we're doing here is really a 2-step process. My first step is to use the ratio test to determine the radius of convergence. And as soon as I determine a radius of convergence, what I find is that x has to be between two values a and b. And our second step is to test the endpoints. And we're going to be testing the endpoints using known tests. So in other words, all of the tests that we've talked about in section 9.4 and section 9.5, we're going to use those tests to see, well, do we truly have equality at these endpoints? Do I have equality at one endpoint? Or is it a true inequality throughout? And so I want to go through a couple of examples here. So the first example I want to do is I want to do the series, the sum from n equals 1 to infinity of negative 1 to the n times x to the 2n over 2n. So again, my first step is I'm going to use the ratio test here. Remember, the ratio test said that we looked at the limit as n increased without bounds of the absolute value of a sub n plus 1 over a sub n. So I'm going to be looking at this for this particular series. So I'm looking for the limit as n increases without bounds of a sub n plus 1. So I've got the absolute value of negative 1 to the n plus 1 times x to the 2 n plus 1 over 2 times n plus 1. And I want to divide by a sub n, which means I'm going to multiply by the reciprocal. So that's going to be negative 1 to the n, x to the 2n over 2n. And so I'm going to need to evaluate this limit. Remember that this ratio test, ideally I want this to be less than 1, because my series is going to converge as long as this limit is less than 1. So doing some reduction, because I'm dealing with absolute values, I really don't need to consider the alternating part of this series. But I do know that this is really 2n plus 2. And so when I divide this x to the 2n, I'm going to be left with just x squared. And in the denominator, I've got 2n over 2n plus 2. The limit as n approaches infinity. Now, this part here is a pretty well established limit. That's going to be 1. So what I really need is I need x squared to be less than 1. And so this gives me the interval from negative 1 less than x less than 1. So that's the first part here, checking the ratio test to determine a radius of convergence to determine a raw interval of convergence. And now we're going to actually analyze this true interval of convergence by testing the endpoints. So when I say testing the endpoints, what I'm doing here is I'm checking where x equals -1. So my series becomes the sum of -1 to the n times -1 to the 2n over 2n as n goes from 1 to infinity. Well, I'm looking at this. This is really -1 to the n times -1 to the 2n. So this is really -1 to the 3n over 2n as n goes from 1 to infinity. And this is alternating. Because for n equals 1, this will be odd. For n equals 2, this will be even. And 2n is going to be positive. And these terms do approach 0 as n approaches infinity. So by the alternating series test, this converges. So if x equals -1, I actually have convergence. And that means this interval of convergence has to include that endpoint. If I check at x equals a positive 1, this series becomes n equals 1 to infinity of -1 to the n times 1 to the 2n over 2n. But this term really contributes nothing to my series. So this becomes the sum from n equals 1 to infinity of -1 to the n over 2n. And this is again an alternating series. It is again each one of these terms without that -1 is positive, and so this is going to converge as well. And so my true interval of convergence actually includes both endpoints. So that gives me something to work with. To find this true interval of convergence, I not only need to find the regular interval of convergence, but I do have to check these endpoints. So I need to actually show my work of how I'm testing each of those endpoints. Sometimes they will work. But notice if I didn't have this -1 here, then this would have ended up being just a regular harmonic type series. I could have compared this using the limit comparison test and shown that it's strict inequalities in this case. So series may look very similar, but actually have different intervals of convergence, at least with respect to their endpoints. But I'd like to do another example of this. So let's take a look at the sum from n equals 1 to infinity of 10x to the n over n. So looking at this, I'm using the ratio test. Remember, step 1 is to use the ratio test. So I'm looking for the limit as n approaches infinity of the absolute value of a sub n plus 1. So this is going to be 10x to the n plus 1 over n plus 1 divided by my original a sub n. So that means I'm going to have n in the numerator and 10x to the n in the denominator. So looking at this and simplifying this algebraically, all of these terms will eliminate all but one of these terms in the numerator. So I've got the limit as n approaches infinity of 10x times n over n plus 1. And I want to know when this limit is less than 1. Now, this part is equal to 1. So 10x is less than 1 whenever negative 1 is less than 10x is less than 1. So x must be between 1/10 and negative 1/10. But now I need to check the endpoint. So I need to check what happens at x equals 1/10. So this series becomes the series as n equals 1 to infinity of 10 times 1/10 to the n over n. And this is really 1 over n. So because this is harmonic, we have to diverge here. And so we do not have equality at this 1/10 endpoint. But if I check the other endpoint where x equals negative 1/10, then I'm looking for the sum from n equals 1 to infinity of 10 times negative 1/10 to the n over n. And this really ends up being negative 1 to the n over n, as n goes from 1 to infinity. And this satisfies the alternating series test. So this converges. And because it converges, I do include this point, and I do not include this point. So my true interval of convergence includes my left boundary of negative 1/10, but excludes my right boundary of positive 1/10. And the reason X excludes it is because it becomes a harmonic series which diverges. So I want to do one more example of this. So I want to take a look at the series, the sum from n equals 1 to infinity of x minus 3 to the n over 2n. So first thing, of course, is I'm going to use the ratio test. And when I'm looking for the ratio test, I'm looking for the limit as n approaches infinity of substituting n plus 1 into this. So this is x minus 3 to the n plus 1 over 2 times n plus 1. And I'm dividing by my original term, which means I'm multiplying by the reciprocal, x minus 3 to the n. And algebra reduces this a bit, so this will reduce all but one of these terms. And the 2n over the 2n plus 1 if I'm looking at this limit as n approaches infinity, this is 1, and so I end up with the absolute value of x minus 3 being less than 1. So negative 1 is less than x minus 3, which is less than 1, and adding 3 gives me 2 less than x is less than 4. So this is my raw interval convergence. I still have to check the endpoints here. That's always step 2, is to check the endpoints. So first thing I'm going to do is I'm going to check x equals 2 and see what happens here. So substituting x equals 2 into my original series, I end up with the sum from n equals 1 to infinity of 2 minus 3 to the n over 2n. And this is really going to be the sum of negative 1 to the n over 2n. And this satisfies the alternating series test, so this converges. So I can include that endpoint. That endpoint is a good endpoint. When I check x equals 4, this series becomes the series from n equals 1 to infinity of 4 minus 3 to the n over 2n. So this is really the series of 1 over n, 2n. So because this is 1 to the nth power, my numerator really doesn't change. And if I use the limit comparison test, I know that this compares favorably to the harmonic series, but the harmonic series makes it diverge, and so I'm not allowed to take that equality. So my interval of convergence includes one endpoint, but not the other. Now please don't get lulled into a sense of saying, well, it's always always going to be the left endpoint because it may not always be the left endpoint. It just happened to be in these two examples. So, what I want to finish up with today is I really do want to kind of talk about how do we determine if series converge, because we've learned a lot of tests, but what we don't really do is kind of know when do we use which test. So that's really what we want to talk about. And so I'm going to talk about step one. The first thing we're going to do is we're going to use our known series. In other words, I'm going to look at cosine of x, or sine x, or e to the x power, or a over 1 minus r. The nice thing about these series is that we know exactly how these behave because we know that these converge. And also the series 1 over x, the harmonic series, because I know that it diverges. So if I can use my knowledge of these known series to show that a series converges or diverges, then I'm done. Now, if this doesn't work, my first rule of attack here is really to look at the nth term test. Because remember, the nth term test says that if the terms are not getting smaller, in other words, if the limit as n goes to infinity of a sub n is not 0, then we diverge. But I don't know conclusively that it converges if it does equal 0. So this takes us to the next step in our term. The next thing I want to do is I really want to look at the p-test. The p-test was really easy to deal with because when I'm looking at the sum of 1 over n to the p, as n goes from some value to infinity, this converges if p is greater than 1, and it diverges if p is less than 1. So I really want to take a look at that and see if that gives me a clue. But of course, this is only going to give me a clue if I end up recognizing this. So maybe I don't recognize that. Maybe I need to fall down to one of the other tests. One of the tests we talked about was the ratio test. Remember the idea behind the ratio test? I'm looking for the limit as n goes to infinity of the absolute value a sub n plus 1 over a sub n. And if this is greater than 1, then we diverge. If it's less than 1, then we converge. And if it's equal to 1, then it's inconclusive. We have this ratio test, and it will tell us if we converge. But remember, the true purpose of this is to determine your intervals of convergence, or a radius of convergence. So that was really the true purpose of this ratio test. But we had other tests that we had to deal with. We had the integral test. The idea that we could take our series and really act as if it were a Riemann sum. So I really want to compare a sub n to the integral of from k to infinity of f of x dx. And they either both converge or diverge. And of course, what we learned back in chapter 8 was that these indefinite integrals were fairly easy to deduce. And as a matter of fact, the integral test is really a more general form of this p-test. The p-test is just so easy to visually inspect the series. But we also had a couple other tests that we've talked about. We talked about the direct comparison test. We also talked about the limit comparison test. And both of these we talked about in our section 9.4 videos. So you can take a look at those too to see how those work. But the other one that we added today was the alternating series test. And of course, the alternating series test was a three-point attack. First, it had to alternate. Second, the terms had to get smaller. And third, the terms had to go to 0. But if this is true, then, of course, we're going to have convergence. And so the question is, what happens if none of these tests work? Well, if none of these tests work, then what we really need to do is we need to look at technology. We need to use algebra or logarithms to try and simplify that. But we're really going to have to try and find some clever way of attacking these problems. Now, if you're using the textbook we're using in class, the Demand Awaits textbook, if you take a look at page 521, you'll actually see this flowchart embedded a little bit more clearly. So this is a wonderful resource to look at if you have any questions about this flow chart. And of course, if you have questions, we can talk about this in class or down below in the comments. I do want to thank you for watching this. We've got one chapter left to go, chapter 10. This has been Mr. Potter. Thank you for watching. Have a great day.